Manish Kumar channel. So today we are going to discuss about subspaces of finite dimensional vector space, and we are going to consider the real vector space actually, okay, in this case. So what is the definition of a subspace? So suppose V is a vector space and you see here V is our vector space defined over real field, okay, and W be any W is called a subspace of a given V if and only if W must be a subset of V first of all. If it means that if you have a vector space V, then you can take, let's say this is my vector space V, right, over real line R, and W can be any subset of it first of all. So W must be a subset of V, and W is a vector space itself. So if these two condition is going to be satisfied, means uh, W first it is subset, first it is subset, and then vector space. If these two conditions are going to be satisfied, then we call W as subspace. W is a subspace of what? V. Okay. So in other word, you can say for any alpha belongs to R in the field element, U, V, any two elements belongs to W, U and V belongs to W, then alpha times of U, alpha belongs to real number, right? So alpha times of U belongs to W, and W is closed under vector addition. So uh, U plus V must belongs to W, right? So these are the two properties. So here V, small v and small w are the element here, right? Small v and w are the element here. Any element you can take, right? List of all elements represented by u, v, w, x, y, z, whatever you like, you can take here. This is a immaterial basically. So you can take here and then say that w is closed under addition and w is closed under vector, scalar multiplication. So the only remaining all the vector space property is automatically going to be satisfied because W is sitting inside of V, right? So we need not to check remaining axioms. We need to only check W is closed under vector addition and closed under scalar multiplication. These two things we need to check, and also we need to see whether W is sitting inside of V or not. Okay, so this is the definition of a vector subspace. So let us see some examples. So examples of subspaces. So you can see here plane through origin. So very quick checking for any vector subspace is very quick checking. As you know already, you have to check two properties, closure and whether subset or not. So very immediate checking is quick checking is always see whether zero vector belongs to W or not. Right? These are just for quick checking whether the given subspace is vector subspace or not, right? So W always, if W 0 belongs to W, then you can check the further properties. If the 0 does not belongs to W, then you clearly declare that the given vector space is not a subspace, right? And also if any U belongs to W, then minus U you have to see. Minus U belongs to W or not. These are the two immediate property you can quickly check for seeing whether the given subspace is whether given the set is vector subspace or not, right? So if this any one of the property is not going to be satisfied, then W is not a subspace, right? This is coming from basically the to is a closure property, okay? So now let us see plane through origin in R3. So if you see any R3, right? So let's say this is X and this is Y and this is Z. So what happened is, let's say if I say X Y plane, right? X Y plane. X Y plane means this plane, right? So this plane is nothing but, you see this plane passes through origin, right? If you see, this plane consists of point 0, 0, 0 also. So 0, 0, 0 belongs to XY plane, right? As I told you, first checking property whether 0 belongs to W or not. So, and W is a subset. So plane is going to be a subset of R3, right? R3 over R, real vector space. Okay. So this is 3D and 2D. Plane is 2D basically, right? So the structure will be of 2D form, R to R over, like, right? So this is clearly a subset of the R3. R2 is a subset of R3, and also zero vector belongs to it. And if you take any u here, if you take any u, which is a which is x comma y basically, right? Then you check whether minus u is here or not. Minus u, if you see, minus u is going to be minus x minus y, right? So minus x minus y will be x negative, y negative. So that point is just will be somewhere here, right? So minus u will also be there, right? So this is clearly a subspace. You can also check alpha times of the remaining two properties, closed under vector addition and closed under scalar multiplication is going to be true. So all those things are going to be true. So this is a subspace. Clearly, this is a subspace, right? Similarly, through origin. Line through origin is going to be also a subspace, because if you see in R3, line passes through origin. Any line passes through origin, right? Okay. So clearly zero vector is there, right? And clearly you see the, you call minus u, then any u you take and then get it multiply by negative sign, you will get it again on the line. So this is clearly a subspace. And also line is a subset of, R3. So all three properties are uh, clearly satisfied. Now the question is, again one more trivial subspace. If we take only 0 as a zero vector, so what is going to be happen? This is a clearly a subspace because 0 belongs to this subspace. Any alpha times of 0 is going to be 0, so this clearly belongs to W. So all vector addition, 0 plus 0 is going to be 0, again is in W. So W is a vector space itself as well as subset of the given V, only single point. So this is also a vector subspace. Now, if I want to say, let's say this is when this is not going to be a subspace, I'll say any line does not pass through origin, right? This line, let's say line 1. Line 1 is not a subspace of given R3. L1 is not a subspace of R3. So clearly this is a subset, right? Line sit in R3 domain. Okay, so this true. But as I told you, check clearly whether zero vector belongs to W or not. So zero vector is not at all in W because origin is here. That's what, if you see, they are mentioning origin in this origin, and this only this zero vector they have taken. So any line which does not pass through origin is not going to be a vector space because zero vector is not belonging to this, because zero vector is not there. You got my point or not? So zero vector does not belongs to L1. So this is not going to be a vector subspace, right? So this is not at all subspace. Any line passes through without does not pass through origin, right? You can see many more also. You see here. Suppose you are in R2, working on R2, right? If I say this set, let's say 0 and 1, this set is clearly a subset of your R2, okay? And then closed under addition property is not going to be satisfied. 0 is also there. I have included 0 here. You see, 0 is also there in that interval. So 0, 1 contains 0 also. So now this is not a vector space because you see here any point if I take u equal to, let's say I take 1, and v equal to, I take, let's say, half. So 1, u equal to 1, v equal to half, both belongs to W. This is I'm calling as W, this space, right? Both belongs to W. But what about their sum? Half plus 1 plus half is going to be 3 by 2, right? Does not belongs to W because 3 by 2 is somewhat outside of the set, right? Which is not even given to you. So this W is not closed under addition. So the logic here is in R2, in R3, in anywhere, the logic is any bounded thing does not work. You got it? Like if you have space, if I'm going to take including 0 also, let's say, any bounded plane, if I give bounded plane is of course a subset of the given R2, right? So this is bounded. So what had happened? Zero vector is of course there, subset is also there, u is there, then minus u is also there, right? But the thing is that when you take two, addition of two vectors is not going to satisfy it, right? So this is not a vector space. If I give you circle equation, right, then it is also not going to be satisfied. So we'll explain multiple cases to visualize geometrically whether the given space is a vector subspace or not. So we can see geometrically like line does not passes through origin is not a vector subspace. Similarly, any bounded domain in R2 is not a vector subspace, whether it consists origin. If it consists origin, then also it is not going to be a subspace. If it does not consist origin, let's say you have some plane here, right? This plane is as W. So this is clearly a subspace of your subset of your R2, but not at all because first property is not going to be satisfied. Zero vector is not at all here. Zero is here, but zero is not there. So immediately checking for vector subspace is zero vector is not in W. You can clearly state that since this is not the case, so this is not going to be true for the given vector subspace. Okay, so the given vector subspace is not a subspace at all, given subset. Okay. So checking property, as I have already explained you, you have to take zero vector and then u and minus u is the very quick checking property, right? Otherwise, you have to prove the two properties, or you have to show all, two properties for a given vector, subspace is a vector space or not. So let us see W. This is x1, x2, x3, x4, and visualization of 4D is not easy, and I'm going to say, let's say any tuple says I'm going to be 0. So here x2 is 0 and x1, x2, x3, x4 all are real number. So whether this is a vector subspace or not, you check 0, 0, 0, 0, all can take 0, 0, 0 also, right? So this is basically if x2 is 0, this is basically three components are left over. So actually 4D and 3D. So W is basically a structure of 3D. So R3 type, okay, which sits in R4. So clearly this is a subset, right? So W is clearly a subset. Now let us check whether a closed under vector addition, closed under scalar multiplication is true or not. So all are going to be satisfied. True, I can say true, right? Zero vector belongs to this, 0, 0, 0, 0, 0 belongs to W, all those things. So if you see this tuple is 0, right? If I say x4 in the same problem, if I update this problem, x4 is equal to also 0, then this becomes R2 actually, right? And which is of course clearly a subset of R4. Then again all properties are going to be satisfied. So this is going to be a subspace, right? Now let us look the next problem, x1, x2, x3, x4 such that x3 is equal to 1. This one is going to make your life miserable. You see here, because anything if you see right hand side is 0, right, with this combination, right, or linear combination you can also say. This combination is going to be 1. So what had happened when you take any two member, let's say 1, 1, 1, 1, right? And another vector 2, 2, 1, 1, let's say. So this clearly, this second tuple, third tuple, they want 1, right? Third tuple is 1. So these are the two vectors in W. What about their sum? What happened? 3, if I take sum, 3 and then 3 and then 2 and then 2. So this does not belongs to W because you see the third tuple they want 1 only, but I'm getting 2. So it is not the part of your W, right? So anything constant here, if I say even constant not equal to 0, x3 is equal to some C where C is not equal to 0, then this is not going to be a subspace. So not a subspace, right? You can design multiple problem with this C constant. Okay. Even you can say x4 as A, x4 is equal to A not 0, x4 x1 is equal to, let's say, B not equal to 0, x3 equal to C not equal to 0. So three different constant you are going to set. So you are going to make measurable of the life of this span, which is not going to be a subspace, right? So this constant term except 0 is not going to form a subspace, right? Now you see here the next example, linear combination of this vector. So as long as summation and linear combination is concerned, this is a linear combination. 2 times of x vector plus 3 times of x3 and 4 plus 4 times. So this is again a linear combination, right? And right hand side is perfectly 0. So this will always work. You can check. So this is a subspace. But look at it, the space, this one, this example. As I told you, this is a bounded domain. You see, this is a bounded domain, right? So what is the structure? You have R3, it will looks like a sphere, right? All the points inside. So zero vector clearly belongs to it, right? But since it is bounded, so vector addition is not going to be satisfied, or scalar multiplication is not going to be satisfied. You got a point or not? So this is not a vector subspace. So any bounded domain does not work here as a vector subspace, right? Again, if you see the next example, product of two term. Product is also not allowed basically. The product of x1, x2 is 0. So this is not a vector subspace. How? Let us take example 1, 0, 0 is one vector. And, you know, I can take uh, 1, 0, 0. I want product of x1, x2. Yes. And 0, 1, 0, let's say. So clearly these two belongs to W. Why? Because this product will give you 0, x1, x2, and this product will give you 0, right? But when we add these two vectors, right? When we add these two vectors, what will happen? 1, 1, and 0. So this does not belongs to W. Why? Because you see this product goes to 1, but they want product equal to 0. So product type, any product type equal to 0 is also not going to be true. Linear combination, any linear combination equal to 0 is going to be true, as you see, you can see previous example, right? So this is not a vector subspace. Similarly, you see this is a linear combination. You can bring this fellow here, x1 minus 3x2 is equal to 0. So linear combination, as I told you, linear combination is always going to be right hand side is 0, is going to be a vector subspace, right? You can design many problem like that. So now again, which one of the following is the subsets are the subspace of P? P is actually set of all polynomials of every degree, right? So P3. P3 is the set of all polynomial of degree less than or equal to 3 is very important. So this is with 0 polynomial. So this is a vector space. Yes, this is true. Now if the set of all polynomial exact degree 3. So let us take example. This is not. Why? We will see. Let us say x3 plus 2x x square plus x plus 1. One polynomial belongs to W. Another polynomial, you can say that uh, x3 plus x square minus x minus r plus 1 is also belongs to W. There are two vectors. U will be a structure of U and V. Will looks like this. U is one vector and V is another vector. You got it? You can assume this is my U, this is my V. So you can write x square, x cube, and this is minus x. So now I'm going to do addition. What had happened if I add, this is gone. So this is 3x square and this is also gone, plus 2. So this is a 2-degree polynomial. What is degree? Degree is 2. You got it? So degree of this polynomial is going to be 2. Degree means maximum power, right? Maximum power of this polynomial. You got it? Maximum power of this polynomial is going to be 2. So x square, you are going to get, if you are going to add, this is gone. This is 2 minus 2 x square only, and this is gone, is 2. So degree of this polynomial is 2, highest power of the x. And what is exactly given? Exact 3-degree polynomial will be in W. So though I have taken two 3-degree polynomial, but it got reduced to 2-degree polynomial, so it does not belongs to W. So W is not closed under vector addition, right? So this is not a vector subspace, right? Okay, and it is a subset because every polynomial of every degree is going to be there, but here this is not the case also, right? So this is not a subspace. Okay, next, if you see uh, which one of the following subsets are a subspace of CAB. What is CAB? Space of all continuous functions which are real valued continuous functions, right? Undefined and close AB. Okay. So set of all polynomials. All polynomials means, it consists of zero polynomial. It consists of polynomial of degree 1, polynomial of degree 2, and so on, right? So see here, this is clearly a subspace. Why? Because if you take addition of two polynomial is again a polynomial of any degree, right? Which belongs to W. And polynomial is a subset of set of all continuous function because polynomials are differentiable, right? So if you see bigger space is given to you CAB, set of all continuous functions, right? Which are continuous. So smaller space is polynomials are differentiable. Polynomials are differentiable of any degree, right? So differentiable function is always a smaller space of continuous functions because some functions need not be differentiable, though it is continuous, uh, right? Space of all continuous functions are differentiable also, right? So polynomial are always differentiable. So this is a smaller subsets, right? Similarly, set of all differentiable functions is also going to be true. All differentiable function, first degree, second degree, third degree, and so on. Anywhere if you reach, this is also going to be satisfied. Set of all bounded functions, right? Because every continuous functions are bounded, defined, and closed interval. This is the result, right? So this is going to be true as well, right? Set of all bounded functions and set of all functions such that fx is equal to 1. This will make your life measurable. What is happening here? If I say f and g are two functions belongs to W, then what about f plus g of x? What happened? Fx plus gx due to linearity. So what happened is 1 plus 1, which is 2, not equal to 1, so does not belongs to W. You got him point or not? So this is not going to be a subspace. So anything as I told you is going to be non-zero is not a subspace. Very clearly you can see. You got it. So similarly, you can see, say, any function. If I say fx is equal to f f2 is equal to, let's say, f2 is equal to 1 also. So at point 2, this is 2 plus 2g. If you take, it's not going to be. So any constant, if I say also, is not going to be true for the given subspace. So you can design many such functions, right? You got it. So check and verify yourself. Verify all of them, okay, whether they are all vector space or not. Okay, so now if you take checking for subspace, set of all m by n matrices with usual addition and scalar multiplication. So here n by n upper triangular matrices which is a subspace of m 2 by 2. You can always see triangular matrices forms a subspace because it is a first of all subsets, and these two properties holds very clearly. Similarly, lower triangular also it is true, right? So this is also a subspace. Okay. Now if you see this example, next example, m2 by 2 is of course a subset of n by n, a b c d, such that a b c d belongs to R and determinant is equal to 1, right? Again I told you, you see, determinant is going to be 1. Determinant 1 means what? So you can take 1 0 0 1. So this is my A matrix, and B matrix you can take -1 0 and 0 -1. This is also belongs, these two are belongs to M2 cross 2, which is my W actually, right? Because determinant is, you see, -1 into -1 become 1 and 1 into 1 become 1. So clearly determinant of A and determinant B are 1. But what about the sum A plus B? A plus B will give you 1 minus 1 0 0 0 0. So determinant of A plus B is going to be 0, which is not equal to 1. So this does not belongs to W. W is here M2 by 2, right? So anything quantities you see here 1 or anything is going to not help at all. Okay. Similarly, if you see, so this is not closed under vector addition. Okay. Similarly, if you see second one, ABCD, such that ABCD belongs to R, such that any tuple is less than. So you see, A greater than or equal to 0, A less than 0, or any tuple says I'm going to be a fixed constant, A equal to some constant C not 0, then these all are not going to be a vector subspace. So answer is no. This is not a vector subspace. Okay. Because why? If I take alpha is equal to, let's say, -1, right? And I do multiply matrix ABCD with alpha, scalar multiplication, where alpha belongs to real line. So what had happened? Alpha times this is affect the life of your matrix. So this is -1 times the given matrix ABCD, right? Minus A means what? Minus A, minus B, minus C, minus D. I least bother about B, C, D, but I want to show you here actually minus A means minus A is greater than 0 now. So what had happened is this, in this given definition, my first tuple must be always negative, right? But if I do multiply with scalar multiplication, then you see this is always greater than 0. So this is contradiction to the given M22. right? So this vector does not belongs to this alpha times of ABCD when alpha is -1 is not belonging to your M2 cross 2, right? So it does not belong. So this is not a vector subspace, right? You can take any of such type A, B, C, set non-constant, non-zero constant, and then it's not going to be satisfied the vector space property. Similarly, if you see, as long as I told you anything is going to be 0, 0, 0 is going to satisfy the vector subspace property. So these all are closed under addition and closed under vector multiplication and so on. Now this is a very important result. Eigenspace as a subspace. You already have seen Ax equal to lambda x. Then lambda is an eigenvalue. Corresponding to lambda, you will get eigenspace that are called eigenvectors such that all vector these are not equal to 0. All those collection of x vector that are non-zero, right? So that means already our job is to figure it out from the given vector space. Vector space V is given. So we are especially searching those vector, let's say x1, x2, and so on, collection of xn. These are the collection. So for a given matrix A, we are trying to search some vectors, some special vectors, some collections of it. Let's say x1, x2, x3, x4, and so on. So I'm going to see some collections, right? Such that x3 is going to be lambda times of x3. I'm going to get multiply by lambda, and I'm going to get exactly the same vector with some multiple of lambda, where lambda is a real number, right? So it can be 0 or 1. So basically, we are trying to see which one of the vector is having the oscillatory behavior. Either it go up or it go down depending upon alpha value. So basically, this matrix is operated on a given vector. What those vectors are, which will provide the oscillatory behavior, right? Oscillates with this matrix. So that collection is your eigenspace, and that is very important in civil engineering for designing of the foundation and all. So they want to see how much oscillation can be beared by the given foundation. Okay. So that is eigenspace is very, very important. And eigenspace E lambda is a subspace of Rn. So if you verify, this is a subspace of uh, given vector space Rn. Okay. Then we'll see key properties of a subspace. Always, as I told you, zero vector must belongs to W. All subspaces of Rn resembles, as we have seen, 0, we have seen R, we have seen R2, and so on. For R3 we have checked. So it is true for all of them. All are the subsets of any set is subset of the set itself. So Rn is also a subspace of Rn. Proper subspace exclude the full vector space, right? So what I'm going to say, 0 and this. So these all are the in between. All the subspaces are called, proper, right? This is full space, and this is trivial. So we don't want trivial and full. We are interested in looking what are the proper subspaces are, intermediate spaces are, right? So that is what we are interested in. And intersection of subspaces is always subspaces. What does it mean? If you have W1 and W2 are two subspaces of a given vector space, then W1 intersection W2 is also a subspace of a given vector space, right? Intersection always be a subspace. Theorem: if a subset S of a given vector space does not contain zero vector, as I told you, zero vector is not contained, then that S is never going to be a subspace, right? Because zero vector must belong to the space, right? Again, one more statement. Let W be a subspace of vector space V such that V1, V2, Vn be the vector in W. Then any linear combination, you see alpha 1, alpha, for any alpha 1, alpha 2, alpha n, any linear combination will also be a space in W. So you can see, like for example, n equal to, if I take 1, what happened? Only V1 belongs to V. right? So a W be a subspace of vector space, and let V belongs to V will be in V, then V1 belongs to W, right? It is given, right? This V1, V2, V3, Vn, if n equal to 1, only V1 belongs to W, right? From this statement. So V1 belongs to W. Since V is a vector space, alpha times of V1 will also belongs to W, right? Closed under vector addition, scalar multiplication. So you can see how it is going to be. So if you see, let's say I'm going to talk about R2, right? So you see here some vector, let's say V is this my vector V1. So this will be given one direction, right? I'm going to multiply by scalar, so I'm going to stretch it. I'm going to stretch it. I'm going to take minus. I'm going to take minus. So what had happened? It will generate the line, right? So line passes through origin is a subspace or not? Yes, we have already seen in the beginning. If V is in this direction, then again line passes through origin becomes a subspace. Okay. Now take n is equal to 2. N is equal to 2 means V1, V2. Two vector belongs to W. If two vector belongs to W, then their linear combination will looks like this. So if you see the linear combination, let's say V is this and W is this. V is this, V2 is this. V1, V2. If I say V1 is this, V2 is this. So what had happened? This direction, this direction. Take the sum. So sum will be this direction, right? Whatever it may be. So you see this is my 2v and v, so sum will be some vector, sum of the vector you can do. Okay, so what happened is it will become in the plane, so it will be somewhere here, so it will generate actually the plane, right? R2 plane. So this is again a vector subspace, right? So similarly, this linear combination belongs to W. It means any linear combination of vectors is a subspace, remains the subspace. That is very, very important statement. Okay. Now, necessary and sufficient condition you can say. So necessary condition here, zero contains zero vector closed under operations like addition and vector multiplication, vector addition and scalar multiplication. Union of subspaces. If union of subspaces are not necessarily a subspace, provided they are contained in another, right? So union will be a subspace if they are contained in another. That is very, very important statement. So union generally is not going to be a subspace. W1, W2 are subspace of a given vector space V. So W1 union W2 need not be a subspace, right? It need not be a subspace. This is not always true. This will be true if W1 contained in W2 or W2 contained in W1. If this is the case, then W1 union W2 is always a subspace. Right. Sum of subspace. W1 and W2 be two subspace of a vector space, then sum is also a subspace because we are adding the points actually. Right. Span of a set. So span of any set of vectors is always a subspace. Right. Trivial and proper. So trivial and proper subspaces. Trivial subspaces already we have seen zero. Proper subspace excludes, remove the entire full space. So these all are the proper subspace. And we are interested in proper actually. This is point of interest, right? Null space and column space. So null space of a matrix M by N denoted by N of A is the set of all solution AX equal to 0, and this is also going to be a subspace of Rn, right? Similarly, the column space means column of the vectors of A, right? Column of the matrix A. So it is denoted as Ca is is the span of the column of A and also a subspace of Rm. So these are two important property. You can also look at it. So now properties of subspaces. So direct sum of subspaces. If W1 and W2 are subspaces of a given vector space such that W1 intersection W2 is 0, then their direct sum is given by V equal to W1 direct sum with W2. This is a direct sum notation. Okay. This means that every vector V in V can be uniquely expressed as V equal to W1 plus W2, where W1 and W2 belongs to W1 belongs to W1 and small w2 belongs to W2, right? So this is very, very important. You got it. And there are some more results which we can see about the W1 and W2, if there are like direct sum or not. So let us see some more. So suppose if you have direct sum, I want to say, so suppose if I have consider the R2 plane, right? So consider R2. So what I'm saying is V is my R2 over R, okay? And you can say W1 means all those points x comma 0 such that x belongs to R, and W2 you can consider all those points 0 comma y such that y belongs to R. So basically I'm saying that this is my W1, this line, and x-axis is my W1. If you look at it here, x-axis, and this is y-axis is my W2, right? You got it. And if I say again one more W3, again one more subspace, x comma x, such that x belongs to R, right? So x plus x comma x means line passes through origin, W3. Clearly all of them are subspace, right? All of them are subspace. You can check it. Okay, because x-axis is line passes through origin in R2, y-axis is line passes through origin, and W3 is also line passes through origin. So now we can write it as, then these are the three subspace, and V can be written as W1 direct sum W2. Why? Because W1 intersection W2 is only zero vector, right? You got my point or not? Zero vector is here in 0, 0, right? So this is the one of the direct sum, right? Again, if I say what about W2 direct sum with W3, W2 direct sum with W3 is also you are going to get V. And what about the W3 with W1? W1 direct sum with W3. So you are going to get three direct sum, right? You got in point or not? So what you can say that complement spaces may not be unique. Complement, because complement, this is complement spaces, subspaces, complement subspaces, or complement subspace, you can say complement space may or may not be, right? May not be unique. Now we are talking about, now one more important point I'm going to talk about, orthogonal complement space, subspace, right? Orthogonal complement subspace, right? So what exactly it does means, if W1, W2 are W1 and W2 uh, or two subspaces of vector space V, right? Two subspaces of a given vector space. Let's say I'm going to say the vector space is V, right? Then V can be written as W1 direct sum with W2, right? Is called an orthogonal complement of a subspace if each vector of W1 is orthogonal to each vector of W2. So each vector of W1 is orthogonal to each vector of W2. So see here, orthogonal complement. So this W1 and W2, any vector if you take, any vector if you take on W1 and W2, they are orthogonal, means 90 degree they are going to make, right? So this is orthogonal complement. Okay, if each vector in W1 and each vector in W2 are orthogonal to each other, means dot product is zero, right? And let us see one more example. But this is not orthogonal. W3 with W1 is not orthogonal. W3 with W2 is not orthogonal, right? And let us see one more example. So if you see here, so for example here, if I'm going to take, so now if I do example, V is, let's say, R3 over R, right? And if we say W1 is all those X, Y, 0 such that X comma Y belongs to R, okay? And W2 is all those X comma 0 comma Z such that X, Z belongs to R, okay? And be two subspaces of a given vector space V, then V can be written as W1 plus W2, okay? But V is not the direct sum, right, of W1 and W2. This is very, very important, right? Another example, you can say like if V is a vector space of all real valued function over R, then it is a direct sum of its subspace, right? If V is a, let's say V is a set of all real valued function, real valued functions over R, over field, right? Over field R, then it is the direct sum of all, then V can be written as the direct sum of all odd function, direct sum of even function, right? This is the direct sum we can always find, right? Similarly, another example, uh, any vector space of all matrices m n cross n, if I say, right, n cross n, B is my n cross n over real entries, okay? So what had happened, this V can be written as the direct sum of all, symmetry matrices m by n symmetry matrices. You got it? All m by n symmetry matrices. So here m by n symmetry, all matrices symmetry matrices, and direct sum with skew symmetry. You got my point or not? So if V is all matrices, then V can be decomposed into the direct sum, symmetry and skew symmetry matrices, right? And if you have, let's say, one more important part, if you have, if uh, W1, W2 and W3, we have three subspaces of a vector space V, right? Such that, such that if I say W1, if I say W1 direct sum with W2, okay, is equal to W1 direct sum with W3, right? Okay, and this is the direct sum, means it will give you V. Then it need not be necessarily true that you can see that W2 is equal to W3. This is not necessarily needed, right? We have already seen in case of your R2, you can see why. So let V is R3, right? And you can say W1 is this. All those A, B, and 0, okay, belongs to R, such that ABC belongs to R. R is better to write in terms of X, Y, Z. So all those X comma Y comma 0, such that X, Y belongs to R, right? W1. What about W2? W2 is all those points such that 0 comma, you can say Y comma Y, right? Such that Y belongs to R, and W3 you can take like this. We have already seen this with example R2. We are going to construct some more in higher dimension. So 0 comma 0 comma Z, right? Such that Z belongs to R. Okay. So you can verify this property, right? So direct sum W1, W2, W3 are three subspaces such that direct sum of W1 plus W2 is equal to direct sum of W1 plus W3. So we cannot conclude that W1 and W2 are equal, right? So this is what we want to say with this example. Okay. So another one more important result I want to make it here for checking your subspace. So since we are working on Rn dimension, so if you have a V as Rn over R, right? Uh, of a vector space over real field, and let's say W1 is going to be your all those points x1, x2, and so on xn, okay, such that xi is equal to 0, right? If I is equal to 1, 2, and so on, n by 2, greatest integer, right? And W2 is nothing but all those x1, x2, and so on xn, such that xi is equal to 0 if I is equal to greatest integer n plus 1 by 2 comma and so on to n, right? Then v is then v can be written as the direct sum of w1 plus w2 if and only if n is odd, right? If n is odd, right, then you can say that the first n by 2 greatest integer n by 2 vectors are 0, and remaining n plus 1 by 2 greatest integer 2n vectors are 0, right? Then v can be written as the direct sum of v plus w1 plus w2 if and only if the dimension is this is the dimension we will discuss later in next video. What is the dimension of a vector space? So if n is odd, right, this will be true only if n is odd. Okay, so this is an exercise for you to verify. So thank you very much. Thanks a lot.